Greetings everyone, and welcome to the next video in my lecture series on differential equations. We are still working on Laplace transforms, and in this video we are doing examples of translations on the s-axis. So we're going to find the following inverse Laplace transforms. Our first example is the inverse transform of 1 over s minus 1 to the fourth. So in a little box to the right, we're going to note that the inverse Laplace transform, the closest we can come, we've got s minus 1 to the fourth, that's a shift on the s-axis of 1, but basically we're looking at s to the fourth power here. So the closest we can come is s to the fourth. We're going to need a 3 factorial in the numerator, and that is going to give us t cubed. So let us take a look at how to handle this. Essentially, so our s minus 1 is a shift of s minus a, and we will multiply by a factor of e to the t, and in this instance a is 1, a factor of e to the at. And in this instance, a is 1, so we just get e to the t. So going back to our Laplace transform on the left, what we really want is we want the inverse Laplace transform of 3 factorial over s minus 1 to the fourth, so that it looks like the functional form that we have inside the brackets over here. And in order to make this equality true, we're going to be dividing by 1 over 3 factorial as well. So we get what we started with, and so we're going to have 1 over 3 factorial, and the inverse Laplace transform of 3 factorial of s to the fourth is t cubed, so we'll still get that. And now to handle the s minus 1, the shift, we're going to multiply by e to the t. We'll do a similar thing for our next example. We're going to take the inverse Laplace transform of 1 over s squared plus 2s plus 5. I'm going to try to make my 5s really obvious, because my 5s normally look like my s's. And we're going to disappointingly note that we've got something that looks a little ugly in the denominator. We cannot factor this. So we can't factor the denominator. If we could, then do partial fractions. So what we're going to do instead is we're going to complete the square. And in order to complete the square, we're going to write s squared. Let me change my color here. So s squared plus 2s plus 5 is equal to s squared plus 2s plus blank plus 5 minus blank. And we want the thing in brackets here to be a perfect square. So we're going to add 1 to it, and then we're going to subtract 1 on the outside to preserve our equality, and then the thing inside the brackets is just s plus 1 all squared plus 4. Let's just draw a little box around here so we don't get confused. Then our Laplace transform that we started with, or inverse Laplace transform, keep forgetting to say the inverse part, over s squared plus 2s plus 5 is equal to the inverse Laplace transform of 1 over s plus 1 squared plus 4. And what we really want, because this looks like the sine term, so let's just do another little box off to the side to remind us that the inverse Laplace transform of omega over s squared plus omega squared is equal to sine omega t. And so what we really want is we want to have the inverse Laplace transform of 2 over s plus 1 squared plus 4, so that the 4 in the denominator, which is omega squared, has a corresponding omega up in the numerator, which means that we're going to have to multiply by a half out front, because a half times 2 gives us the 1 that we had initially, and so that's going to be 1/2, and we're going to have a sine of 2t, because omega here is 2, and then we're going to have to account for the fact that we have the s plus 1 here, so we're going to be multiplying by an e to the negative t.